Hi, welcome back to the breadboard. Today is Monday the 30th of May and it is day 2 of the Texas Instruments Internet of Things week. Yesterday we had a look at various launch pads and selected the CC3200 launch pad for the base of our project, where we're going to build an IoT node that will be measuring temperature and light and sending it out onto the internet to the cloud to be stored into an MQTT server. We will also ultimately be having a subscription to that via Node-RED and displaying with graphs and various other things the data that's being collected onto a smart device. That could be a phone or a tablet or even a PC. Anything that runs an HTML5 browser would be sufficient to be able to view this. Anyway, today we're looking at temperature and how to monitor it. We're going to look at very quickly go over a few different devices that I have, and then we will take a little bit of a deeper dive into the one we're going to use for this project and have a look at how we hook it up to the CC3200 launch pad so that we can use it in our project for the rest of the week. Now, to start with, I'm just going to be outputting the data we collect through to the serial port so that you can see it functioning without having to worry about any of the other devices we're going to add on through the week. Anyway, let's get to the bench and have a look at some of the devices I've got down here for us to evaluate. Not all of them are from Texas Instruments, and of course we're going to pick one for this week from Texas Instruments because it is TI week after all. So let's go have a look. Okay, so we have quite a range of temperature sensors that I have available to me in the lab here. We have some NTC, negative temperature coefficient resistors, which are these ones on the right hand side. This particular one is contained within a metal shroud. It's more of an industrial kind of thing, but basically it's just an NTC. Another one that you may be familiar with, which is another NTC, is the kind that you find with PCs for measuring the CPU temperature and things like that. And you find these in batteries as well to measure the temperature of a battery. They're very common. The next kind we have here coming along, I'm actually going to skip over here, is two sensors that you may have seen before. These are DHT22s. This one's a DHT22 and a DHT11. These are actually temperature and humidity sensors. Again, not made by Texas Instruments. These use a one-wire protocol and typically will work on 3 to 5 volts. The next one I have here, which is back to an analog one, it's in a container. It comes in a TO92 can or a SOT, basically a flat pack to go on a surface mount, is an MCP9701 from Microchip. The next one we're going to look at going down the line is another one-wire chip. This one's from Maxim, and it is a DS18B80. This is another version of a one-wire device, and I've got them in a number of different formats, right from tiny surface mount chip up to TO92 packaging. This one's on a wire, so I can easily plug it into one of my devices. You also can get them in a industrialized package, same as the NTC one I just showed you, where it's got a little stainless steel cap, quite easily will handle being dipped in fluids and various other things. The next one we're going to look at is a range from Texas Instruments now. Everything else we can look at is now from Texas Instruments. And the first one is I've got a TMP107 temperature sensor. Now these are in their anti-static bags. These are also small surface mount. The TMP107s are a one-wire serial communications, and their nice thing about these is that they're a 14-bit resolution, 0.4% accurate over a range of -55 to +125. I think it goes up to about 0.7% accurate if you want to go across the entire range. But if you go from about -20 to +80, it's down to about 0.4% accurate. The next one I have, TMP006. It is actually a non-contact temperature sensor. It's I2C connected, and as I say, in this case, it's built onto the board here. And then we have the TMP006 that's built onto the boards. We've got the TMP108, which are basically a variation of the 107, except these are using a full I2C bus. 0.75% accurate, -40 to +125 degrees centigrade. They come in these nice, as I say, a nice little surface mount packages. Next one we're going to look at is the TMP275. This is 12-bit accurate, and I actually have one already mounted on a little breakout board here so that we can use it. And it's got a minus 40 to plus 125 degrees C range, it's I2C interface, and a 0.5% accuracy. So this one is the one that we're actually going to end up using because it's very straightforward to drive. It's got an I2C interface, which means it can be directly controlled by the CC3200 without having to get into any fancy timing. It's all handled by the hardware. So now let's go and look at how we will integrate this into the CC3200, and we'll look at the Energia code that we will use to read the sensor data and output it to the serial port. Okay, so this is the CC3200. Yesterday when we selected the board, we really didn't have a close look at it. We just had gone over a lot of the high-level specs and everything for it. So this is the actual user guide for the CC3200 Launchpad. You can get this from the Texas Instruments website. I'll provide the link in the description with the post. And this basically tells you all about the Launchpad itself, how to use it, bit of an introduction. Key features is it's internet on a chip, it's got built-in Wi-Fi, 40-pin Launchpad, which is the XL standard. We just scroll down a little bit. This is an overview of the board, and you can see here we've got the USB connection at the top. We've got two sensors built onto this board that we're not actually going to be using this week. One of them is a 3-axis accelerometer here, and the other one is a contactless infrared temperature sensor. Coming down, we've got the main CC3200 processor right here, and on the left and right hand side we have the main connectors that booster packs and other devices will attach to, and we're going to use these connectors on this side to wire up our TMP275 temperature sensor. There's LEDs at the bottom, and the two switches are user controllable if you wanted to. The temperature sensor that we're using, let me just switch to that data sheet for a second. This is the one we're going to use, 0.5% accurate TMP275. Uses an I2C interface. And so what do we need to interface to this? Let's scroll down to the chip. So the 2-wire host controller is going to be our CC3200. And you can see here that to connect to the chip, you've got the SDA, which is the data line for the I2C bus, and the SCL, which is the clock. The other line here, the alert one, is if you set some temperature thresholds inside this TMP275, you can have it actually generate an interrupt to the microcontroller, independent of actually the controller having to poll it and read the temperature and things. The A0, 1, and 2 allow you to set the I2C address of the chip within a certain range, and then you've got the plus supply and the ground. Now, because we are connecting this to a 3.3 volt CC3200, then we need to make sure that we connect the V plus to 3.3 volts, not to this maximum of 5 volts. Now, that's pretty much all we need from here for the moment is this pin out for the TMP275. And like I said, I've plumb mine onto a breakout board because these are surface mount, and I have some fly-in leads soldered onto it so that I can just plug it into the headers that are on the CC3200. So let's go back to that. All right, so here we go. Now with the CC3200, you can see here clearly the user guides, all of the Launchpad user guides, by the way, are as clear as this. You can see down here where the I2C connections are, this SCL being the pin 9 and STA being pin 10. Okay, now these second row of pins, which is called P3 here, is 21, 22, 23, 4, 5, 6, 7, 8, 29, 30, and then pin 31 is over here on the inside. So yeah, pin 22 ground, pin 1 3.3 volts, pin 9 SCL, pin 10 SDA. Those are the only things we're going to be using, and we're going to connect up the TMP275 where 3.3 volts to pin 8, pin 22 goes to pin 4 on the TMP275, SDA, which is pin 1 of the TMP275, goes to pin 10 of the Launchpad, and then the SCL, which is pin 2 on the TMP275, will connect to pin 9 of the launch pad. For this exercise, those are the only connections that we're going to need to use. So the next thing to do is to go to Energia and have a look at how we start setting this up to talk to the TMP275. On the CC3200, pin 1 is going to connect to pin 8 on the TMP275. Pin 9 is connecting to pin 2. 10 to pin 1 and 22 to pin 4, and pin 5, 6, and 7 of the TMP275 are all tied to ground to set it to its default first address. That completes it, aside from the USB connection to the PC so that we can send out serial data. That's all the wiring that is required for this particular phase. So now let's go look at the programming. So to start with, because we're using I2C, you need to include the wire.h, which is all the libraries that are built in for handling the hardware I2C port. We are using the TMP275 temperature sensor, so we have to set the addresses for the I2C bus and also various settings within it. We'll look at the datasheet for the TMP275 in just a moment. So TMP275 is address 4F. It's we want to run it in 12-bit mode, which is 0x60 that we send to the control register for doing that. We will be reading from temperature register, which is a register 0, and the control configuration register is register 1. These next three parameters are just used for calculating the temperature degree C from the data that we get back from the temperature sensor. We're going to have a couple of routines. I don't like using delay functions, because they stop everything from working within the code. I would much rather have a main loop running and doing nothing, just triggering the other routines and functions as and when the time expires for them. So that's what I'm going to do. So in the setup, it's very, very simple. We start off the serial port, and I'm just setting it to 115K baud. We call wirebot.begin to initialize the I2C bus, and we call a function called init temperature. And init temperature simply sets up the temperature sensor to work in 12-bit mode, and then it resets the control register to point to the actual temperature register, so we can just keep reading from that afterwards. Once that's done, we just continue through, and then the underlying application, which is part of the compiled app that goes up as a standard C program, will then continuously call the loop function from a while function outside in its main loop. So this is just going to loop continuously as fast as it can, and all it's going to do is update the temperature and update the serial port. That's all as far as the loop is concerned that it's going to be doing. But if you look at the update temperature function, what it does is if the temperature time is less than mils, then it will do this function, and temperature time is defined at the very top here when the program starts. And you can see here that we have a delay value of 1000. That could be actually changed to a const if I want to, which means 1 second basically, and then the temperature time is set to the milliseconds, whatever the current milliseconds value is, plus the temperature delay. So basically it says in 1 second we're going to do something. And so when we're in this update temperature, it says if 1 second, basically it reads as if 1 second has gone by, then read from the temperature probe address 2 bytes. If there's something come back, well, wait till something comes in, then read the 2 values. Now here we're doing a little bit of shifting, and we'll look at the data sheet and you'll see where this comes in, because we get a 12-bit value from a 16-bit register. So when it reads the 2-byte temperature, it's actually set up in a special way because it's only 12 bits, but it's contained within a 16-bit register. So the upper byte, the first byte that comes in, what we do is we shift it left 4 places to make room for the remaining 4 bits into a temperature value, which we're not actually defining here because I'm actually using it directly in a function called to calctemp. So we're setting up basically a 16-bit value. The upper part is the 8 bits of the first byte shifted left 4 bits, and the lower part is the second byte, where the lowest significant 4 bits are actually irrelevant and want to be get rid of. So we shift that byte right 4 bits, and then we OR them both together. We end up with 12 bits of data, with the upper 4 bits being 0. and we call the calc temperature, and then that returns a value in degrees centigrade. And all that does is every second it will then call that routine, and it will update the value from the TMP275. And you can see at the end of the function, it resets the timer to another 1 second delay, or whatever that value is set at the top for it to be. So it would be easy to change it to some other interval if you wanted to. The second thing that the loop does is simply update the serial, which is another function. And if you look at that routine, it basically structurally is the same as the update temperature, where it will look at the serial time, and if it is elapsed, basically by comparing it to the current milliseconds, it will do the function inside, which in this case is just simply printing the current milliseconds divided by 1,000. So it basically tells you the elapsed seconds since the unit was powered up or last reset. And then it will print the double, which is a temp C, and then just simply put a C after it just to indicate it's centigrade. And then it just resets its timer, and then it goes back as well. So basically what we have is we've got two time functions going on. One which is defining how often do we update the temperature, and one which is defining how often we output it to the serial port. Now in this case they are both set to 1 second just for the sake of this. We're not doing anything else in here because that's for other days of the week for the IoT week. That's all we're going to do. So let's just have a look before we run this. Let's have a look at the data sheet just so you can understand a little bit of what I'm doing. Just skimming through the data sheet here, and we're looking at the temperature data format. These are only the 12 bits that are coming out in 2 bytes. So these first 4 bits are the upper byte. These next 4 bits are the upper nibble of the second byte, and the lowest 4 bits are ignored. You can see here though that it's a 2's complement, i.e. it's a signed value. So this most significant bit is actually a 1 when the output is negative and a 0 when it is positive. So you have to factor that in when you're calculating the temperature. So here are the registers of the TMP275. The first one here showing is the pointer register. So when you write to the TMP275, the first thing you write along with the address, the first byte would be where you're going to write to with the next command, or where you're going to read from. By having all zeros in these, well, all of these are zeros, only the least significant 2 bits are relevant. So a 00 points you to the temperature register. A 01 points you to the configuration register. That's where you can set 12 bits or less and various other functions. And there are 2 other registers, a T low and a T high. These 2 are where you can actually set a temperature threshold for a low alarm and a high alarm. We're not actually using that in this example, but I just wanted to point that out. So here we're looking at the temperature register. So here's byte 1 of the temperature register, and here's byte 2. And you can see here that it's clearly showing that D0, 1, 2, and 3 are all physically wired to 0. These are the insignificant bits that come out, and actually only T0 through T11 are the ones that are relevant, and T11 is actually the sign bit. The configuration register here is telling us things like the resolution, the polarity bits, and various other things. The descriptions for each one are here. Oh, here's RO and R1, by the way, the resolution of the TMP275. We're using it in 12-bit mode, which means that the fastest you can actually do of any relevance is 220 milliseconds and a resolution of 0.0625 degrees C. If you go back to the command register up here a second, at the very top here, one shot OS. This allows you to actually tell it only to do a single conversion at a time, but you have to keep telling it to do that. We're running it in continuous conversion mode. Now, one of the things you might use for this, if you're using an ultra-low environment where you're running on batteries and you want it to run for a long, long time, and if you're just measuring environmental temperature, probably only measuring the temperature once every 5 to 10 minutes is probably more than enough in most situations. So why have it powered up for all that time? So what you would do is you'd set it into one-shot mode, set it into standby, and then every 10 minutes when the CPU wakes up, it'll just tell it to do a one-shot conversion and then shut it down again. In our case, we're just going to let it run in continuous mode. I think the only other significant thing I want to mention right now for this, the TMP275 can also share the I2C bus with many, many other devices. Because you've got 3 address lines that you can configure for this, that basically means that you can have 8 devices all on the same bus. with ease, all of the same type. Now the thing to remember with I2C is that you need to have pull-up resistors. Now in my case, because the CC3200 already has two I2C devices on it, there are two jumpers on there which you can actually use to disconnect those devices, but if you leave them plugged in, then it also provides two pull-up resistors. Okay, so let's go back and now have a look at the program again. So here is the program, and you can see on the right hand side it's busy chugging along because I've already uploaded it. So we've got the, as I said, I'm not going to run through the whole program again, but you've got your initialization, you've got your setup routine, which starts the I2C bus and then initializes the temperature controller, which is the TMP275. We have a very, very simple loop, which is probably going to be running through thousands of times a second. Update the temperature, update the serial port, and it just repeats that. And the update serial just outputs the data if the time has come to the serial port, and if the time hasn't come, it just drops right back out and returns, so it wastes no time. The update temperature basically does the same thing. If the time has not elapsed for updating the temperature, it'll just drop right out. If it has come to the point where it's ready to do another read, it'll read from the temperature sensor and return the data into the calling routine, and return the temperature into the global variable, and then it will exit. Now, the one thing I wanted to just mention about the calculate temperature is we've got two things here. The first function here, the if temperature raw and OX0800 is concerned, is looking at the sign bit. Remember, we've already adjusted for the 12 bits into the lower half of the unsigned integer. And the 12th bit is the sign bit. So if it is set, we are reading negative temperatures. If it is not set, we're reading positive temperatures. This one is adjusting for 2's complement with a sign bit, and this one is just taking the absolute value of the integer and returning them. And that's pretty much it. You just compile this, and you just hit the upload once, as long as you've got your CC3200 plugged in. Click the serial port. Now I have it set for 115K2. The default is often 9600 down here. So if it's giving you weird data on the screen, then just adjust the baud rate to match what you've set up in your setup right here, and then it should display properly. And there it is, displaying nicely the temperature. Every second it's doing the update. So in tomorrow's video, which will be Tuesday, we're going to introduce the Sharp LCD booster pack. This is the 430 Boost-Sharp 96. It's a launch pad booster pack. It's sold by Texas Instruments, but it's actually a Sharp LCD display. That's for tomorrow, so I will see you then.